Welcome to our sixth lesson on electromagnetism. We'll be looking at how to calculate the induced EMF today. Now, when calculating our EMF, we are going to be making use of Faraday's law. And he stated that the induced EMF would be equal to the rate of change of magnetic flux. Now, whenever you get to the word rate of during a definition, that means divided by time. And in this case, it's divided by time for the change of the magnetic flux. Now, change in means your delta value, and that means your final minus your initial value. So it's in this case the final minus the initial value of the magnetic flux divided by time. But those are not the only components that we'll find in my induced EMF formula. We will also take a look at the number of coils or windings that we would find on this conductor. But let's first trace a few steps back and see what is EMF and what's the symbol and the unit in which we measure it. Now, the symbol for my induced EMF is a capital letter E, or sometimes they make use of a small letter cursive type of E. And then also the unit will be V for potential differences, which is also volt. Now, our formula is our E, that stands for our EMF. The N stands for the number of windings. That basically means how many times this coil has been wrapped around. And you'll note that there's a negative in front. I'll explain the negative in a short while. Let's just continue on with what the rest of the formula indicates. We've got delta, in this case not Q but V, and that means to us our magnetic flux. But it's the change in magnetic flux. And change in means the final magnetic flux minus the initial magnetic flux as it was moving through a magnetic field. And then we've got our change in time. Now, that negative sign in the front of my number of winding is there so that we can take a note that when we've got a current and a magnetic field, that it will oppose the change in magnetic flux. Now, when it opposes this change in magnetic flux, it basically means that we will then end up having a value in an opposite direction, which would be negative. Now, therefore, we'll be placing in our negative sign, and that's the same as what you've learned with Lenz's law when you determine the direction of the current when you had a bar magnet being pushed inside of the solenoid and being pulled out of the solenoid. We said back then that your current would be always created by the fact that it induces the change to it. So that, for example, meant that if you decided to take a north side of the pole to be pushing it inside of the solenoid, the imaginary magnet that will be formed inside of the solenoid would oppose that change and therefore form a north on the side where you'd like to enter with your north pole. But because it then forms this north, it then opposes the change being done to it. And that's how come we place this negative sign in the front. Now let's go and take a look at an example and explain step by step how we'll go about calculating this induced EMF. So we're going to be having a 100 millimeter diameter coil consisting of 150 loops, and it's placed in a perpendicular magnetic field with a magnitude of 0.45 Tesla. The magnitude of the field then changes to 0.3 Tesla in 0.7 seconds. And they tell us that the total resistance of the coil was 0.1 ohms. So we will be moving this coil from a magnetic field of 0.45 Tesla, that is my initial situation, to a magnetic field that is 0.3 Tesla, and that's then the final situation, and that's done in 0.7 seconds. Now, the question first off asks you to go and calculate the induced EMF. Now let's go and take a look at our formula. Our induced EMF is indicated by our E here, and then it's equal to negative the number of turns, and multiply the change in magnetic flux divided by the change in time. Now, we do have the number of turns, that's 150, and the time as 0.7. But our change in magnetic flux value we do not have. When we go and take a look at our magnetic flux, we note though that that's still equal to your magnetic field times the area times cos theta. So we would need to make use of my magnetic fields given initially and finally together with the area of my coil, and that will then end up giving me my magnetic flux. So we're going to do two calculations, that of my initial magnetic flux and the final, and only then can we go and calculate the change in magnetic flux. Good, so my initial magnetic flux is my initial magnetic field times the area times of cos theta. Now we would note that we've got our 0,45, but once again we do not have the area of the coil. It has been given though that the diameter of this coil is 100 millimeters. But when we want to go and calculate the area, we'll use the pi radius squared, and therefore it means we'll need to take half of the diameter so that we can have the radius. Good, so calculating in this case my area, we'll take the 100 millimeters divided by 2, and then we'll still need to divide this value by 1000 to get our millimeters to meters. Now, our answer will end up being 7,85 with a few decimal places times 10 to the power negative 3 meters squared. This is not my final answer, so we're going to be leaving this value unrounded off. Now, our angle between, in this case, the normal of the coil and the magnetic field will be 0 degrees, and that means cos of 0 gives us 1. So our initial magnetic flux ends up being 3,53 times 10 to the power negative 3 Weber. In calculating my final magnetic flux, we'll be using our magnetic field of 0,3. The area of the coil is still the same, our 7,85 with all its decimal places times 10 to the power of negative 3, and we would still have our angle between the normal of the surface and the magnetic field to be, in this case, 0. And then our final magnetic flux is 2,36 times 10 to the power of negative 3 Weber. Now we're going to be making use of my final and my initial values then to go and calculate my change in magnetic flux. Now once again our change in means the final value minus the initial value always, and that ends up giving us a final value for my change in magnetic flux of negative 1,17 times 10 to the power of negative 3. Now we're going to leave this negative with my answer and carry it over to the last part then of the calculation. So it's a negative 150 windings in this case. My change in magnetic flux is a negative 1,17 times 10 to the power of negative 3 divided by the change in time, which was given as 0,7. And my final answer is the 0,25 rounded off to 2 decimal places volts. Now the last part of the question asks us to go and calculate the magnitude of the induced current. Now remember, in your calculation, or the part of the question did give you the resistance of this coil to be 0,1 ohms. And you've just calculated the potential difference to be 0,25 volts. So you can go and calculate the current using our formula of V is equal to I times R. So we will be using our 0,25 volts in order to calculate our current that will multiply with the resistance of 0,1. So to calculate my current, we'll take the 0,25 divided by my 0,1 and end up with 2,5 amp as my final value for my current. Now the question which I would like you to go and attempt tells you that a coil of 400 loops experiences a change in magnetic flux from 1.4 Webers to 0,7 Webers in 0,4 seconds. Go and calculate the induced EMF. So first pause your player and attempt the question before looking at the answer.